computer and share screen. Okay, so we were discussing calculation of Basal functions, basically numerical error. The subject of this chapter is to be aware of numerical error. And as a good example, we said that calculating Basal functions looks very simple, but you will see soon that in practice, this might not be that easy. So we have this recursion relation, how to calculate J, this is so-called this is so-called recursion relation with two of the second order. So if we have L and L minus one, we can calculate L plus one, or if we have L and L plus one, we can also calculate L minus one. But we need to have two in order to calculate the third one. And we also know the initial condition, J0 and J1, and therefore looks pretty trivial to calculate J for any L. And that's exactly what we're going to do, so-called upward recursion. We're going to calculate JL from J0 and J1 for arbitrary X and arbitrary L. Now this code is available both in GitHub and also on our webpage. So I have this code in Jupyter Notebook. We will discuss more about details of Jupyter Notebook. You can use either Jupyter or can use just the Python scripts if you want to. It doesn't matter right now. I will use Jupyter Notebook because it's kind of easier to write comments next to it. So in Jupyter Notebook, one thing that you can do is you can write nice text next to it. So there are two types of cells. One is code and one is markdown. Well, and a few other things. But markdown is basically comment. So, and this hash here means type of title. So more hashes means subtitle, subtitle. One hash means title. And you can write LaTeX equations. That's one nice thing, that LaTeX equations show up as text. They're being rendered. So that's a nice thing about Jupyter Notebooks. So what we want to do here is we want to evaluate this recursion formula. Starting from J0 and J1, we can calculate J2 and so on. So this little code here is supposed to do exactly that. Let me see if I can increase this a little bit, the size. Yeah, okay. So I'm importing from Skype, I'm importing everything, okay? So in most of codes, people tend to not import everything because this is a little bit dangerous. So if you have a very large project, you might not want to use this from Skype import star, because this means that whatever symbol exists in Skype will also exist now in my environment. Okay, so if Skype defines a variable pi, then my pi is now defined in my local scope. Now, this is basically what I want, because I'm really math symbols from me, such as pi. I don't want to say this is from numpy pi, doesn't it? I want to have it in my global, in my local environment. But once you have lots of different modules, there is sometimes useful not to include it in this way. But in many times, people in the community do for example, import numpy as np. Okay, so this is much more standard. Import numpy as np, which means that any symbol that appears in numpy is supposed to be called with np dot something. Okay, however, if I import it from numpy import star, it means that any symbol that is inside numpy does not need to be prepended with this symbol numpy. Okay, because, for example, even if I wanted pi, I would need to write numpy.pi. Okay, which is kind of awkward. So I can do import numpy as np, and then I could use, instead of numpy, I could use np.pi. Now, only if I use from numpy import star, then I can just use pi. Okay, so in most of this class, I will use this most global import in the sense that I import everything from SciPy. Now, in previous versions of Python, I would just import everything from SciPy and that's it. Why? Because SciPy already imports everything from NumPy, and there is no need to import stuff from NumPy. However, there is a little issue that somehow appeared recently. Namely, it seems that the community has ported a lot of things from SciPy into NumPy, and lots of symbols like zeros appears, symbol zeros appears in NumPy and SciPy. And right now, the two functions are basically identical. They do the same thing, but the code issues a warning saying that SciPy will discontinue this symbol in next version. So you get lots of warnings. The code works, but it gives you lots of warnings. It says SciPy zeros has been discontinued. Please use NumPy zeros. Okay, and that's kind of awkward. I don't want to have a lot of warnings when I have my freshly written code. So if you import on top of SciPy, you import everything from NumPy, then NumPy symbols override the SciPy symbols. So if it turns out that certain symbols, such as zeros, is defined both in SciPy and NumPy, NumPy will overwrite, and you will get rid of the error. All these things are a bit dangerous in some sense, but currently I think this is kind of the best way to have all mathematical symbols in your local scope and avoid all warnings or errors. At least I haven't seen any errors in this way. So again, from SciPy import star is just it imports all the symbols from SciPy to my environment, and from NumPy import star is right now a hack, kind of hack, so that I don't get warnings, which recently appeared because there are certain symbols that appear both in NumPy and SciPy. Okay, so for that being said, we're going to define now this Basal functions, a function that calculates Basal functions with upward recursion, which takes as an input L, which is the maximum L up to which we need a Basal function. And X is, of course, value on axis, floating point value, for which we want to evaluate Basal functions. Okay, so first we will allocate, or basically initialize, a Python, NumPy array for L+1 values. Why L+1? Because the last value that we need is Basal function of L, of order L. Since Basal functions start with order 0, it means that if we need order L, there are L+1 Basal function evaluations, isn't that? Because if you need Basal functions of order 2, we will have 0, 1, and 2, which are 3 of them, doesn't it? So therefore, we need space for L+1 Basal functions. So this is going to be the output. And then we're going to say if absolute value of, if X is very, very small, then we know what the result is, because only Basal functions of order 0 is finite. This is something that we know from, from definition of Basal functions, or from, let's say, old books, that Basal function of 0 is basically sine x divided by x, isn't it? Which means that when x goes to 0, this goes to 1, but all higher order Basal functions go to 0. We can calculate Taylor expansion. Basal function of order 1 goes as x, Basal function of order 2 goes as x squared, Basal function of 3 goes as x to the 3, and so on. We could, of course, do the Taylor series and calculate this more precisely, but once x is less than 10 to the minus 30, we don't need Basal functions, let's say, with precision more than 10 to the minus 30. I mean, this is more than good enough. Even the standard libraries don't give you Basal functions more precisely than that. So therefore, if x is very small, all we know is that Basal function 0 is 1, and all the rest of the Basal functions are 0, but they're already set to 0 at the beginning. So after that, we can immediately return, doesn't it? So if x is small, at this point, we're done, okay? One thing that's important to take care of in math is always take care of the limits first. So for example, when x is very small, you have to take into account this special case first. Why? Because otherwise, if you start to evaluate recursively something for very, very small x, you will have lots of numerical problems, okay? So therefore, the special cases should be treated first. Okay, now if x is not so small, then we can evaluate J0. You see that if we didn't take care of special case when x is very small before, we would have an issue even to evaluate J0, isn't it? Because we're dividing 0 by 0, basically, isn't it? 0 by 0 is indeterminate, ill-determined. But now that x is finite, we can evaluate this, J0, and then we can write this J0 into the first as a result of the first in the first slot in array. We can set it there, and then if the user asks for only up to L is equal to 0, we are done. We can return. Okay, we don't need to do anything else. However, if L is bigger than 0, then we need to do something else. What do we need to do? Well, then we need to evaluate J1 as well, isn't it? We can calculate J1, and analytically is given as J0 divided by x minus cosine x divided by x. We know that this is the value of J0, J1, and then we set J1 into the right place in the array. Okay, so up to now, we have calculated J0 and J1, and we write them into the array, okay? And now we can start recursive. So we can now go, we know exactly for how many steps of recursion we need to do, isn't it? Because, or iteration, basically, it's just iteration, it's not really recursion. So we start with L is equal to 1, and we go with up to I is less than L. Okay, so first I is equal to 1, then we evaluate what? 2I plus 1 divided by x times J1 minus J0. See, this is this recursive relation. 2I plus 1 divided by x, Ji, which is J1 in this case, minus J0 is equal to JL plus 2. So J2 is now JL plus 1. Okay, and then once we evaluate this, we store this value of J2, we store it, and then we overwrite J0, J1 by J1, J2. Okay, and we can then repeat this. Okay, and we just need to, you need to convince yourself that not only this starts at the right with the right JL, but it also ends correctly in the sense that the last value that we store is actually JL. Why? Because I is always less than L, which means that the last L is equal to, last I is equal to L minus 1, and then we write this into I plus 1, which means that the last value that's being written is a res of L. And that's exactly what we need, doesn't it? So it ends correctly. Okay, so let me evaluate this now. Okay, so now we have this function evaluated in the memory, and now we can start using it. Okay, so here I prepared test for this recursion, and in order to use in order to check how precise this calculation is, we're going to use Basal functions, which is defined in the library of special functions. So if we import from SciPy so-called special module, module contains, among others, Basal function under the name spherical Jn. Okay, so if we are interested in this module, let me check first from SciPy import special, and then I can do help of special spherical Jn, and this is supposed to show us what this function is. You can always use help on any Python symbol. And it says that this is a spherical Basal function. You can give you n as an order special function, and z is the, of course, value. It can be complex. We're going to use it on real numbers, but in general, it can be complex number. And then we can also calculate derivative at the same time if we want to. We are not going to do this. By default, we don't calculate derivative. Special Basal function of the first kind and its derivative. And well, there is, yeah, basically this is also computed from the recursion relation. So basically the library does exactly what we are doing. So we expect similar precision, I guess. Okay, so let me cut this out. Okay, so I'm importing this special Basal functions, and I'm going to calculate this Basal function for all these values of L from 0 to L at particular X. And I'm going to also calculate these values with my upward recursion. So that 0 will contain now our values of Basal function with upward recursion, and that one will contain the one from the library. And the question is, how close are these two? We can, of course, just, these are both are arrays, so we can take the difference of the two arrays and we can call them diff, and then we will see how big the difference is. Now I'll do this for particular case of L is 10 and X is 0.1 to show that the error can be pretty substantial in this case. Let me evaluate this. Okay, so what I get is the following. So this is that 0, which is our calculation of the Basal function with upward recursion. This second one is the one from the library, and the difference is here displayed. Okay, so let's look at it. Well, as you see, the difference for L is equal to 10 right now is basically of the order of 90. 90. Okay, that's huge. So the right value, for example, for L is equal to 10 and X is 0.1 is 7.2 10 to the minus 21, while our recursion gives us 93 and something. Okay, so the two values have nothing in common. They're so wrong. They're several orders of magnitude wrong. I mean, 22 orders of magnitude wrong, isn't it? That's how wrong it is. Unbelievably wrong. And this is only Basal functions order 10. Okay, it's really not that many. This is only basically 10 levels of 10 operations, isn't it? So within 10 operations, we basically lost 22 orders of magnitude. That's enormous. Okay, why? Well, because this iteration is just horribly unstable. Okay, so let us go into details and try to understand what went wrong. So for this, we realize that we actually need so-called downward recursion because the upward recursion doesn't work. But let me demonstrate. That. So here I prepared just one step of the recursion to get you a feeling what goes wrong. So let's say that we have Basal function. Well, let's say that we have the exact value for Basal function of order 9, of order 10, and of order 11. Let's say at X is small, when X is small. Okay. So the question is, can we do even one step of this recursion precisely? Okay. And what happens when we do one step? So let us try to do the upward recursion, just one step. So what do we do when you do the upward recursion? Well, we calculate J11 from J10 and J9. Okay, and the way we calculate is this: 2 times 10 plus 1 divided by X times J10 minus J9. Okay, that's what we do for upward recursion. Now, why does this work so badly? What's the problem? What's the fundamental problem? Well, the fundamental problem, as we discussed last time, is that we subtract two numbers which are almost identical. That's the problem. So in order to demonstrate this, I will print here the first part, the first part of this equation, 2 times 10 plus 1 divided by X times J10. So this is part 1, and then I'm going to also print part 2 of the upward recursion, which is minus J9. Okay, and what we're going to see is that part 1 and part 2 of the upward recursion are basically identical, and they subtract almost completely. And since they subtract, well, what we're left is enormous error. Now, however, if we do the downward recursion, then it's a different story. We're calculating from J11 and J10, J9. Okay, that's what downward recursion means. So we have J11, we have J10, and we need to calculate J9. Okay, so how do we calculate that? Well, J9 is being calculated by the same expression, 210 plus 1 divided by x times J10, but then we subtract J11 rather than J9, doesn't it? Okay, is it clear? So now we can also the same way check how much these two numbers subtract. Do they subtract or they don't subtract? How does it work? Well, in order to do this, we need to, of course, compare how big is J11 compared to this first part. Okay, and I will evaluate this, and we see. Well, part 1 in this particular case is of the order of 10 to minus 27. And part 2 for the upward recursion is almost exactly identical with opposite sign. So of course, when you sum these two numbers, they subtract, and what we're left with is something of the order of 10 to the minus 32. So we go from two numbers which are almost identical. They're both of the order of 10 to the minus 27, and the difference is of the order of 10 to the minus 34. So in other words, in this step, we are subtracting 4, 5, 6, 7. We are subtracting 7 orders of magnitude. So the two numbers which have 7 digits equal. Okay. So in one step, you're basically losing the precision, which is of the order of one floating point number. Okay. And basically in two steps, in two such steps, you're going to lose 16 digits roughly. So it means that you cannot do more than 2 steps and you lose all precision that double has. Double has 16 digits. Okay, you're going to lose them in basically 2 steps. Okay, so that's how unstable this thing is, and it's all because the way this works is that we need to basically subtract two numbers which are almost identical, and you can see that smaller is the x, worse this gets. Okay, if x is 1, then it's not so bad. So let me try x is 1. You'll see then it's okay. These two numbers are still close. You see, they're both 10 to the minus 9, but they're only first 3 digits are the same. Okay, first 3 digits, and then it's okay. So we're losing 3 orders of magnitude every time we make a recursion. But since we have 16 digits, we can still do 10 operations and still don't lose all the precision. Although it's already bad. But once x is small, such as 0.1, then we are losing enormous amount of precision every time we do operation, isn't it? And smaller the x, worse it gets. Okay. But the good message is that when we do the downward recursion, then basically we need to sum up this first part and part 2 downward. Now you see that in this case, the two numbers don't subtract. It's not a problem, isn't it? Because one number is several orders of magnitude bigger than the other one. So that these two numbers are easy to add, isn't it? So we can always gain precision in this step rather than lose precision. Okay. So the worst problem is when you have two numbers which are almost identical and they subtract, but then the information that we keep is almost nothing. Okay. So this demonstrates you that when x is small, the rule is when x is smaller than L, then upward recursion doesn't work, but downward works pretty well. Now, if I take x to be large, then you will see that it's the other way around. So when x is 10 and you try to do, well, in this case, they both work, because when x is equal to L, both work roughly, because this is the borderline. But if x is very, very large, for example, then upward recursion should be safe, but downward shouldn't be so good. So in this case, upward recursion, you see these two numbers are not close at all. So upward recursion is safe, but the downward recursion should be problematic, because this number and that number, well, it looks okay right now. still looks okay. So it's interesting, still looks okay. Maybe if X is even bigger, this should become problematic eventually for downward recursion. No, for downward recursion should become problematic. Right now I don't see it. But the usual story is that when L is equal to X, that's where kind of both upward and downward recursion are borderline. If X is smaller than L, you have to do downward recursion. If X is bigger than L, you have to do upward recursion. Okay. Now, how do we do downward recursion? That's a little bit tricky. It's a so-called Miller algorithm. So downward recursion somehow, of course, is just that we calculate the smaller L from L and L plus 1. We calculate JL minus 1. But how do we start? So because the recursion relation is linear and homogeneous, so linear means that we don't have any squares of JL here or cubes or anything non-linear. So they're all in linear terms. And then the another important thing is the homogeneous, which means that you don't have any particular constant added. Okay, so means that so it's obvious from this equation that we are allowed to multiply the entire equation with the arbitrary constant 2, constant 10, constant 100, whatever, with arbitrary floating point number or even complex number, and we get a sequence which still satisfies exactly the same relation, isn't it? So we are allowed to multiply all accumulated values of JL with an arbitrary constant, and they still represent solution of the same recursive relation. So the same recursive relation is still valid even when we multiply all JLs with a constant. That's obvious, isn't it? Because this is homogeneous linear relation. Okay, so now with this, once you know this, it's kind of obvious that we can always calculate the entire series up to a constant. So series can be 100 times too big or 100 times too small or 1,000 times too big, doesn't matter. And then when we get to evaluate J0, we just normalize the entire series in such a way that J0 is correct. Okay, so the idea is very simple. You evaluate the series, let's say downward, by starting with an arbitrary value, because it doesn't matter what you start with. Okay, and then once you come down to L is equal to 0, well, then you realize what the normalization constant is. You multiply the entire series with this normalization constant, and your series is correct. All JLs are correct, except maybe the very, very high ones. Now, what we're going to do is we're going to start at some large L, so L max, which is bigger than L that we need. We need to start somewhat higher. We're going to write JL max plus 1 is equal to 0, and JL max is equal to 1. That's how we're going to start. Now, again, this 0 and 1 are somewhat arbitrary. It doesn't matter how you start. Okay? What we do know, the important information that we know is that JL falls off with L. So in other words, each value, for each value of L, higher value of L will be smaller and smaller and smaller. Okay, that's the information we need to have. And in this case, this is true. So therefore, for some large enough L, we can set it to 0 without loss of accuracy. Okay, because let's say that JL max plus 1 is going to be 10 to the minus 23, for example. Here we see that the J11 is 10 to the minus 23. Okay, for our precision that we need, this is equal to 0. We can equally set it to 0. It's fine. Okay, so we set to 0 the last value, but then the previous value can be set to an arbitrary finite number. It doesn't matter what it is. Now, of course, the entire series will depend on this number, but at the very end, when we get down to L is equal to 0, we will renormalize the entire series in such a way that that J0 is going to be correct, which will guarantee that all other L are correct, except maybe a few which are for the highest, close to L max, higher up. Okay, so is it clear that this algorithm should work? Anybody? Do you understand the algorithm? Is it clear? No? Not clear? I don't hear anybody.
It's clear to me.
It's clear to you. It's easy, isn't it? Yeah. So once more, it's very, very simple. So we have an information that Basal functions for small x, for which this is valid, fall off with large L. So in other words, for some large enough value L max, we can definitely set J L max plus 1 to be 0, okay, because the values fall off. And without loss of accuracy, we can set some L max, JL max plus 1 to 0. And then with JL max, we can choose an arbitrary constant, arbitrary. We will set it to 1, but it doesn't matter what it is. Why? Because at the end of the day, we will renormalize the entire series in such a way that J0 is correct, which will guarantee that all other JLs are correct. And we can do this because the series is homogeneous and linear. You know from math that this works. Okay, so okay, so now once we understand the algorithm, the code is actually pretty simple. It's really not hard. The only thing that we need to know somehow, that somebody needs to well, then we will probably need to experiment a little bit, is how to choose L max. So given an L that we need, let's say that we need L is equal to 10. So what would be a good L max? It has to be somewhat bigger than 10, maybe 20, maybe 30, I don't know. It has to be bigger than L. Because we want to start high enough so that by the time we come down to L, the precision is already pretty good. So the reason that we can use this type of algorithm is because by doing recursion downwards, we're actually gaining precision with every operation rather than losing precision. That's interesting because we're gaining precision. So the question is, what is good L max? And it turns out this is something that you can see in numerical recipes, that a good starting point for L max is actually L plus square root of 10 times L. Okay, so let's say L is 10, then we need to go 10 times 10 is 100, square root of 100 is 10. So basically roughly 20. So if L is 10, we need to start with L is 20 and go downwards. So this is a good starting point that you can find in old books how to. Of course, if you want to have even higher precision, you might need to increase this numbers a little bit. But with this, I think we're going to get 10 to the minus 16 precision roughly, which is more or less what we are interested in. Okay, so again, if x is very, very small, then we do the same thing as before. We just return we know the Basal function of 0 is 1, all the rest are 0, so we can return the entire array without doing any calculation. But in general, we do need to do this downward recursion. So we start with some large L, then we set J2 to 0. This is what I said before. JL max plus 1 is set to 0. Then J1, which is JL in this case, is going to be set to 1. And then we are going to iterate down. So first we prepare an empty array, an empty list, actually, Python list. And then we're going to save in the Python list only the values which actually we need to return, not all of the values that we're going to calculate. So, and then what do? Well, we calculate the previous value, basically JL minus 1, which we're going to call it J0 right now, from JL and JL plus 1. So in this case, it's interesting that this relation looks almost identical. So 2i plus 1 divided by x, J1 minus J2 becomes J0. Okay, so the expression looks almost identical to upward recursion. But then, yeah, so here we store only the values that we actually need to return. So in other words, when I becomes small enough, smaller than L, that the user wants us to save, then we save this value. Otherwise, we don't. So in other words, we're going to disregard the first few values because these few values are being just calculated at the beginning in order to get rid of the error. But once L becomes equal to the I becomes equal to the input L, to the L that we actually need to return to the user, then we start saving. Okay. Yeah, this step actually just is part of the recursion, which means that we now set J2 to J1 and J1 to J0. Yeah, sometimes we actually do this in one statement. It's maybe easier to do this, J1, J0. It looks nicer to me, but it's the same, isn't it? Maybe this is a little bit slower, but it doesn't matter. This looks nicer, isn't it? J2 and J1 become J1 and J0. Okay, and okay, so up to now, we now saved all the values from L down to 0, okay? But the important point is that the first entry in this res right now is JL, next one is JL minus 1, and then finally the last value is going to be J0, isn't it? So they are actually saved, the way we save them here, are saved in an opposite direction that we expect them. We expect J0 to be first, not JL, isn't it? So because of that, we're gonna use something which is called reverse. So this reverse just basically flips the first and the last element, doesn't it? And all of them. Okay. So this is just that from now on, we're gonna have J0, J1 to JL. Okay. And now all these values here are fine, but unfortunately, they're not properly normalized. Okay, we said that these can be orders of magnitude wrong. The series is correct, but the values are wrong. Why? Because we didn't normalize them yet. So what we need to do is we need to calculate the true J0, which is sine x divided by x. And then all we need to do is to normalize in such a way that the J0 is correct, which means that all other values are going to be correct. So what do? We create from this list a Python array, NumPy array, and then we multiply with true J0 divided by the value of 0. So you see this array res divided by res of 0 is equal to 1, and then we multiply with true J0, which means that the first entry is going to have correct value. It's going to be J0, which guarantees that all others are correct as well. Okay, so evaluate this. Do you understand the algorithm? Is it okay? You can think of it a little bit later, but it should be pretty straightforward. Okay, so now we are gonna do the same experiment. So L is 10, X is 1, let's say, and we do the downward recursion, and we also calculate the exact values, and then we subtract the two difference, and we see that the difference actually pretty good. 10 to the minus 16, 17, 17, 25. Pretty good. That works. This is for X is 1. What about X is 0.1? Even better. You see, the difference is 10 to the minus 33, 35, pretty precise. So the downward recursion clearly works for small x. Of course, it should not work for very large x. Yeah, for very large x, we start to see pretty large differences, doesn't it? So large x doesn't work, but small x works. So if x is 1, definitely works. Okay, so now we understood that basically that the downward and upward recursion can be valid for different values of x over L, doesn't it? So now we need to combine the two together. So if we experiment this a little bit, we're going to see that when L is equal to X, that's where the critical value of L and X is. That's where we need to break the series from upward to downward. Okay, and this code basically does exactly that. It uses um, upward recursion where possible, where upward recursion is stable, and downward recursion where downward recursion is stable. And it kind of glues together the two. Okay, so what does it do? Let's check. If L is less than X, okay, so if all the L's that you need are less than X, then we know that upward recursion is stable everywhere. Okay, and we don't need to do anything else. We don't need to bother with downward recursion. So if L is less than X, of course, upward recursion is slightly more efficient, less operations. So if L is less than X, we just return upward recursion and that's it. Now, however, if L is bigger than X, which is very common because X can be small, then we need to calculate the value of L critical, which is equal to X, but integer value of this, isn't it? Basically, this assumes that X is positive. If we want to generalize this to negative X, this needs to be made absolute value of X, integer of absolute value of X. But for now, I didn't care of negative X's. So L critical is then integer of X. This is typecasting a floating point number to integer value, and then we can say that that we can do what? First, we do the downward recursion. Just a second. If L critical is less than 0, yeah. So if it turns out that that X is very small, so that L critical becomes 0, which means that X is between 0 and 1. If X is very small, then we know that only the downward recursion is fine for every L, okay? Because X is very small, so the critical L is 0, then we can do the downward recursion only, okay? Now, however, if none of this is true, then we have to combine upward and downward. So what we do is we first calculate upward recursion up to L critical minus 1, because we know that in this case, upward recursion works. This is for small L. But then for large L, we substitute, we calculate the downward recursion for all L's, for the maximum L down to 0. But then we know that only part of this downward recursion has to be saved. Okay, so only from L critical on, this part of the array is precise. The rest is not precise and we need to use the upward recursion. So here we are basically stacking together the upward recursion up to critical L and then the downward recursion from critical L on. Okay, so from L critical on, we are using once more downward recursion and upward recursion for small L. Okay, so this combines the two together. Yeah, this H stack means horizontal stack, stacking together the two NumPy arrays, which are yeah, of certain size, so we can stack together, create a new array out of those two. We're going to discuss the details of Python later on. For now, you kind of need to get some feeling of how Python works, and we're going to go into details probably even today of precise meaning of this H stack here. But for now, you just remember that you have two NumPy arrays, you put them together into another array. Okay, so this creates the combination of relation Basal function for upper and downward recursion. And now we're going to test this. So let's say that L is 10, X is 5. We calculate upward recursion, downward recursion, then calculate the combination of the two, and then finally from the Basal functions using the library. And now we're going to check the difference between the exact value, .a is the library, minus .2, which is the combination of upward and downward recursion. And then here it's only, here is the precision. Dot E is basically exact minus dot 0, which means it's upward recursion. So we're checking precision of the upward recursion. And then here we are checking precision of the downward recursion. And if we evaluate this, we can see that if we have this combination of downward and upward recursion, then precision is basically always of the order of 10 to the minus 18. Now, the upward recursion becomes slightly less precise for a large value of x, while downward recursion somehow is still okay. Now, if we put small x, for example, we expect the upward recursion to be disaster, and indeed it is. Downward recursion is fine, and this combination is also fine because it just uses the right one. Now, if we take x is very large, for example, then we see that downward recursion is bad, and upward recursion is good, and the combination of them is also good. So, and x is 10, basically both should work. Upward and downward recursion are both reasonable. Downward 10 to the minus 12, upward 10 to the minus 16, and the difference is also reasonable. So the point is that with proper combination of upward and downward recursion, we can get then value Basal function for every L and every x. Okay. Now, to demonstrate this, I'm going to plot now values of Basal function in logarithmic plot for a large value of L's and X's. So how do we do that? Well, we're going to use pileup. So again, we're going to go into details of this pileup later on, but basically this is the Python library to for plotting. And for now, we're going to just use this. We're going to globally import every symbol from pileup into our environment. So we do from pileup import star. We globally import everything in pileup. And then this is a special line which magic keyboard which is relevant only in Jupyter notebooks. So if you are using your Python code, you're just coding in Python editor, you should not use this this line. Matplotlib line is only relevant when you are inside Jupyter notebooks. And what does it do is basically says that all the plots which normally would open up another window should appear inside my notebook. Okay, so once more, this keyword here is only specifies that I want my plots to appear inside my notebook in Jupyter notebooks. Okay, so it's only relevant when you're doing when you're developing things in Jupyter notebooks. Otherwise, you skip this line. All the rest is identical in Python or Jupyter notebooks. Okay, so what we're going to do then is we're going to take L is 15, and then we're going to take X between very small number like 10 to the minus 6 to 50 with 100 points. So we're using 100 points between 0 and 50. Okay, so here this plot is supposed to demonstrate this. So X goes from 0 to 50, and in y-axis we are plotting Basal functions. And we have all kinds of L from 0, 1, 2, 3 to 15. Okay, so what we're going to do is we're going to evaluate upward recursion for all values of x. So for t in x, okay, for all values of x, we calculate upward recursion. So this now becomes array of arrays, which is a two-dimensional array. Okay, so we're calculating with upward recursion all Basal for all Basal functions for all x. Then we do downward recursion for all Basal functions for all x. Then we evaluate the combination of upward and downward recursion. Okay, and finally, we're gonna use the library to calculate the value, which is kind of more precise. Okay, the exact, whatever we call exact value. Of course, this value here from the library is also not infinitely precise. Also, usually it's 10 to the minus 16, and that's it. It's not more precise than that. Okay, now we can plot. So we're going to use a plotting function which is called semi-log y. So this semi-log y means in x-axis we plot in linear scale, and in y-axis we use logarithmic scale. Why? Because we want to, we want to show the error bar. An error bar is of the order of 10 to the minus something, or large 10 to the plus something, and we want to use linear scale in x. And we're going to plot absolute value of the error. Okay, so first we're going to plot a combination of up and down recursion. So this is .2 minus .e. So this array, .2 minus .e. So we're taking the difference between the exact value and the value which is obtained by upward combination of upward and downward recursion. Okay, so this is the first plot. Let me evaluate this. Okay, and you see, this is error when we do a combination of upward and downward, the way we break it. And well, basically for all else and all x, this is close to 10 to the minus 16, with one exception. One value here, one error bar is 10 to the minus 12. But this is still very, very small. Okay, so in other words, for basically all else and x, we are pretty much set. We have very precise value of Basal functions. Okay, with this trick. If you want to get even better, you might need to debug a little bit when this happens. Most likely, I think probably we need to start slightly higher with the downward recursion. We would need to start from slightly higher L if you want to get even higher precision. But let's say that this is good enough. 10 to the minus 12 is pretty good for what we need. This, of course, is absolute error bar. I think that relative error bar is also pretty good. It's like we have at least 6 to 7 digits for every value of x and L. Now, of course, we can do the same for downward and upward recursion, checking them separately. And you can see now for downward recursion, for small x, this is very good. But then when x becomes large, of course, the error starts to grow pretty badly for downward recursion. Well, not so badly, but still it's not, these values become large. And the trouble is that this is the absolute value, the absolute error bar. It's not the relative error bar. Relative error bar is enormous because the values tend to be small at large x. Okay. Now, with upward recursion, we also see how it works. For large x, it looks fine, but for small x, it's complete disaster. So the relative error, the absolute value error becomes enormous. I mean, maybe it would be better to show here relative error rather than absolute error. Maybe demonstrates better, but this already shows you that the two directions work very differently. Now, there are some strange spikes here in these plots. Do you know why these spikes occur? Well, it turns out that for some particular x values and some particular L values, the difference between calculations in the library and my calculation is basically 0. So whenever the value is 0 and we plot in the logarithmic plot, this is like minus infinity, isn't it? So there are some lines here, but basically it just means that the error is below 10 to the minus 113, which can occur sometimes. Okay, so this is supposed to demonstrate how quickly error in calculation can damage our numeric calculation, and therefore we have to be very careful about how to implement an algorithm. So you see, this algorithm, basically, all we had to do was just turn around the recursion relation, and the precision became orders of magnitude better. So these are the tricks that we have to have in mind whenever we do numeric evaluation. One, way might be unstable, the other way might be more stable, and you need to play with it. Now, for the homework. Of course, this particular script is available online. You can download it. I mean, it's in GitHub if you want to, but it must be also here into introduction. Yeah, it's under GitHub. And it's also here, computes Basal functions with upward and downward recursion. So you can download it here, you can download it in GitHub, and you can play with it. Now, there is, however, a homework that I want to give you. So at the end of this chapter, there is something which is called homework. It said second, I don't know, first one, I guess, was installation or whatever. I mean, I already gave you several homeworks, but this is now the first real homework, okay, which I want you to return it in hopefully within a week, if you can. So what do we need to do for this homework? Yeah, first, are there any questions up to here for Basal functions? Any questions?
Actually, there is a question.
Okay.
Well, can I go back to the Jupyter notebook?
Yes.
And go to the Basal J function. The function combines. Yeah, exactly here. So actually, my question is, well, maybe not that relevant here. So my question is, why you have an underline ahead of your variable GU and GD?
GU and GD, this one.
Yeah.
Yes. Why
you have an underline behind it?
Doesn't matter. This is just
okay.
my choice of the variable. Probably JU and JD were already used, so I put an underline. It turns out that in Python, what they use many times is this symbol, which usually means a kind of local variable that it doesn't need to be. How can I say? It usually means somehow local, irrelevant variable, temporary variable,
Okay.
Okay. Temporary, yeah. But it's completely irrelevant. I mean, it can be anything.
Okay, I see. Yeah. Thank you for clarifying. Yeah.
No problem. Any other question? Is it too simple? And no questions? Okay, so then let's go back to homework. So that's gonna be the first real homework. So what I want you to do, it looks, I mean, the homework is more or less, is very similar to calculating Basal functions, okay? But it's somewhat different in the sense that the recursion relation is different, okay? So I want you to write Python script to compute, well, okay. So first part of the Basal function is write Python script to compute spherical Basal functions with up and down recursion, plot the error of algorithm when compared to Skype version JL. So basically the first part is basically just repetition of what we've done, nothing new. I mean, you can download it, you can play with it, you can use it, okay? So this part is completely trivial. Now, I mean, this optional, you can do it if you want to play with it. It's not important, but you can do it if you want to. You can use F2Py or PyWint11 to speed up the algorithm if you want to. Again, this is just from your own practice. I'm not going to even check this part. It's optional, okay? But this part is something that I want you to do, okay? This is the new part. This is somewhat non-trivial. So I want you to compute the series of integrals defined by this relation, okay? Kn can be calculated with very similar recursive relation as Basal functions, okay? Now, the homework has two parts. First is to figure out what is the proper recursive relation, and second is to implement it. Recursive relation is somewhat similar to the Basal function, but it's different. It turns out it's linear, but it's not homogeneous. So it has a little bit of extra complexity, okay? But don't worry, I will show you the solution here. So you don't need to spend an entire weekend trying to figure out how to solve that, okay? So now, where's the problem? So we want to evaluate this integral for n0 up to some n max, let's say 10, just like we do for Basal functions. And for simplicity, we will set a and b to some numbers that you don't need to do it for every a and b. Let's say that a is 0 and b is 1. So in other words, this integral goes from 0 to 1. Okay, let's simplify this. You don't need to test for every a and b. Now, we want to derive first the recursion relation between kn plus 1 and kn. So it turns out that in this case, we have a recursive relation only between, so it's not second order, it's only first order. So if you know kn, you can calculate kn plus 1. However, the trouble is that this recursive relation is also unstable in the sense that you can do it only in one direction, either upwards or downwards, depending on alpha over z. So if you start from the first one for k0, you can calculate kn up to some n max using the recursive relation, of course. This works quite well for alpha over z is bigger or equal than 1. However, if alpha over z is much smaller than 1, if it's of the order of 1, it's still okay, this works. But if it's much smaller than 1, let's say 10 to the minus 4, we will see that this recursion does not work. It's actually pretty disastrous as well, similar than in Basal functions. And then in this case, we need to implement the downward recursion, very similar as before. Well, in this case, we're going to check, I guess, alpha over z is less than 1/2. So it turns out that when alpha over z is 1/2, it's roughly where you need to switch between upward and downward. Okay, so make sure that you start with a very accurate value of kn max. You can derive a power expansion of kn max in power of alpha over z to the k and evaluate as many terms as needed to achieve desired accuracy. For example, 10 to the minus 12, and then use that. Okay, so this is the problematic part. The point is, this recursion that we are going to get is not homogeneous. And because it's not homogeneous, you cannot use the trick that you use for Basal functions, namely to multiply the entire series with an arbitrary constant. You can't do that. So what you need to get, however, what you need to do in this case is to evaluate kn max for some value of n to the largest n that you need, you evaluate with very high precision. And in this case, it turns out you can evaluate it with Taylor expansion. So it works. Taylor expansion works very well. And then you can use downward recursion to evaluate all other n's. Does it look scary? The homework? Okay, so I'm going to help you because I don't want you to be scared. Let me find the solution. Where's the solution? No, this is not the solution. You know this trick, this thing?
I was all over the news this morning.
Yes, exactly. That's not what I wanted to show you, okay? I want to show you the homework solution. Yeah. Okay, so here's the solution. We need to evaluate this thing. It turns out that this actually is important when you write functions such as Green's function. You expand Green's function in terms of Legendre polynomials. So this actually integrals do appear in physics quite often. So how does it work? Look, the idea is that we write the numerator in such a way that we add something and subtract something. Okay, so we have here we are writing kn plus 1, which has on the numerator x to the n plus 1, isn't it? Okay, so what we can do is we can write x plus z over alpha x to the n minus z over alpha x to the n. You see that this first part, z over alpha x to the n, subtract. Is it obvious? Okay. Do you see that this is exactly kn plus 1? Is it obvious? Okay. So in other words, this z over alpha x to the n here. Okay, let me use annotate. Yeah, annotate should be useful. Text draw. stamp spotlight. Just a second, draw. Haven't used this before. Let me try to draw something here. So what I want to say is that this part here and this part here, these two subtract, isn't it? So in other words, we are left with x to the n plus 1, which is exactly the kn plus 1. Okay, so that's how we start. And then what we do is we figure out that actually this thing here and this thing here cancel, isn't it, for the first term? Okay, so therefore, what we're actually left with is x to the n. So this first part is basically just x to the n. You see this part? Okay, and the second part is, well, the second part is exactly kn times 0 or alpha. You see that? Okay, so we managed to write kn plus 1 in terms of some prefactor times kn and something that we can definitely evaluate. Is it clear? Clear or unclear? So once more, we write this part and this becomes this. Okay, and then this part here, we realize that it's just kn with a prefactor 0 alpha. Okay, clear? And basically this is all we need. So then this integral x to the n is something that we learned in high school how to do, is bn plus 1 minus en plus 1 divided by alpha n plus 1. Okay, so this we can evaluate, and then this we just copy. So now we are going to do this for b is equal to 1, a is equal to 0. So it's a bit easier. So then this thing is basically 1 divided by alpha n plus 1, and this thing is 0 alpha kn. So we arrive at this recursive relation. Okay, is it clear? So this is our final recursive relation. Okay, so the problem here, you see that this is just the first order recursive relation. So from kn, we can calculate kn plus 1. The issue is that this is not homogeneous. So I cannot calculate, I cannot multiply the entire series with a constant c, for example. If I do that, this wouldn't work, isn't it? Because this is non-homogeneous series. It's linear, but it's non-homogeneous. So non-homogeneous cannot be multiplied with an arbitrary constant and keeping the solution of this recursive relation. So therefore, we cannot decide that we're gonna normalize the series at the end. But we need to start with precise enough value of kn plus 1, of the maximum kn. So if we need the upward recursion, then there is no problem. We can evaluate k0. K0 is very simple. K0 is logarithm. You can evaluate this for n is equal to 0, isn't it? N is equal to 0. This is logarithm of z plus alpha x. Okay, very easy. From k0, you can calculate k1, you can calculate k2, you can calculate k3, and so on. Okay, but when alpha over z is less than, let's say, 0.5, then only downward recursion is stable, and we need to use this recursion. So from n plus 1, we can calculate n. However, as I said, this particular recursion relation does not allow you to renormalize all the values in the series. You need to start with precise enough value of this maximum kn plus 1. Okay, so how do you do that? Yeah, so because recursion is not homogeneous, it is linear, we cannot multiply all terms with arbitrary value. So what you need to do is the following. We need to use a Taylor series and evaluate the first value for large n with a Taylor series. So in other words, you need Kn for some large n of n. Okay, so Kn for some large n of n. So I now rewrote the definition for Kn, which is here, slightly differently. You see, this is exactly the same as Kn. Kn is written here. And I rewrote Kn in exactly, well, in an equivalent way. I took z out, which makes this alpha over z times x here, okay, -1. And you see, why did I write it this way? Because now I can Taylor expand, or it's kind of ready for Taylor expansion. And the important point is that alpha over z, this thing, is smaller than 1. Okay, we're using this in the limit when alpha over z is smaller than 1. Actually, at the end of the day, we're going to use only smaller than 1/2. And at the same time, x is also smaller than 1, because the integral goes from 0 to 1. Okay, so in other words, this entire thing, alpha over z is smaller than 1/2, x is smaller than 1. This entire thing is smaller than 1, smaller than 1/2. Okay, so since this is small, then you know that the Taylor expansion works well. Okay, so what do you do? Well, this is the Taylor expansion of this thing, minus alpha over z x to the m. This is so-called, what is it, geometric series. And now, if you go from m is 0 to infinity, this is the exact value of Kn. You can calculate it for any n, exact value. Now, of course, we are not going to go to infinity. We're going to go to some large n of m, but not exactly infinity. And we're going to evaluate how big m needs to be. But the important point is that this integral now is really trivial, because we have x to the n times x to the m. This is x to the n plus m, and this integral you can do. I mean, it's completely trivial. The value of the integral is x to the n plus m plus 1 divided by n plus m plus 1, isn't it? And then you evaluate this in with the upper and lower border, and this is the result. Again, we're going to set b is equal to 1 and a is equal to 0 for simplicity. Okay, so basically, setting b is equal to 1 and a is equal to 0, we get this recursive. This is not recursive. This is Taylor expansion. So this is Taylor expansion, with which we can also calculate when alpha is when alpha over z is less than 1. We could just use this this Taylor expansion for every z and for every n. Okay, we could use that. However, it's not very efficient, especially if you need lots of n's. This expansion needs lots of terms. So once you calculate this for one n, large enough n, then it's much more efficient to use the recursive relation that we specified before. Okay, so therefore we're going to use this Taylor expansion only for the maximum n that we need. Okay, so then the only question is where to start. So for alpha over z less than 1, the terms beyond some large m are arbitrarily small. Okay, so you should be able to see that this thing falls off for large enough m. Why? Because alpha over z is less than 1, let's say less than 0.5. We're going to choose 0.5 to be the value where we're going to start to use this. So alpha over z is small number, and we have to put this to the power of m, and m is also a large number. So we have something that is much smaller than 1, and we put to some large power. So that has to go to 0, doesn't it? That's very, very small. So therefore, for large enough m, this value should be small, and then we divide by n plus m plus 1, it's also small. So the whole thing should be small. So therefore, when this capital M is large, we can be absolutely sure that we can stop the Taylor series, isn't it? Okay. So the question is, however, how large this M needs to be. Well, we can evaluate, we can estimate what's the value of the last term. So by using a little bit of math, you can see that if you go to M, which is logarithm of epsilon divided by logarithm alpha over Z, where epsilon is the precision that you need, this is where you can stop. So epsilon is the precision with which you need to evaluate Kn. So let's say that you set precision epsilon with 10 to the minus 16, then this will give you roughly the maximum value of M up to which you need to go. Okay, so so basically you evaluate maybe 10 or maybe 20 or maybe 30 of those terms in a Taylor series, and then you have your maximum Kn. Once you have that, the downward recursion is completely trivial, isn't it? You just go down with recursion. Okay, so I see. So now I need to use the eraser. Okay. Yeah. So this is implementation. My implementation takes just basically one page, so not a big deal. Implementation is something that it shouldn't be too hard, in my opinion, for you. But here is sketch. So basically, I take this cutoff in precision to be, let's say, 10 to the minus 8. Doesn't need to be that precise. So let's say 10 to the minus 8 is small enough. And then I'm gonna take another cutoff, 0.5. Basically, I'm gonna say if alpha over Z is less than half, then I use one versus the other direction of recursion. Okay, so if Kn, just a second, if alpha over Z is, yeah, if absolutely, so X in this case is alpha over Z, minus alpha over Z actually. So I write first, when the user gives me alpha and Z and alpha, I calculate X, which is minus alpha over Z. And then I say if absolute value of X is less than 0.5, okay, then I can use, I need to use what, for small x, I need to use, I guess, downward recursion. For large x, I can use upward recursion. So upward recursion is completely trivial, okay? That takes no time. The K0 is just the difference of two logarithms, and then I just fill in the array with this recursion. I take Kn minus Ki, and I calculate Ki plus 1. Completely trivial. So upward recursion is takes no time. Downward recursion is a little bit more tricky. So if x is small, then I need to do downward recursion. So what I do is I first spend this few lines to do the Taylor expansion. Okay, so I go for m in range some large number. So I first say that I'm going to calculate thousands of those Taylor coefficients, but of course in practice I never do that. So in practice I calculate only a few. So I evaluate one term in the Taylor series. It's an arbitrary term in Taylor series. I add to the sum for the Taylor series. Then I calculate x to the n. So rather than doing x to the n, I just multiply previous xn with x. And then I say that if the contribution of this last term, so last term in the Taylor series, is small enough, like 10 to the minus 8, then I break the loop. So then I'm done. And so in practice, this loop will not take many iterations. So that's one way of calculating how high up you need to go. The alternative is to do some math and estimate how far you need to go. But you can also just break. So you say that if the last contribution is small enough, I believe that my value of Kn is good enough. And then I save once I have this value of k for the largest n, I saved it, and then the downward recursion is completely straightforward, isn't it? It's just yeah, it's just this difference, actually sum of two terms. Okay, so is this clear? Clear enough? Anybody?
Yeah.
Yeah.
Yeah, that's great.
So shouldn't be too hard, huh? So once more, remember that basically this recursive relation is probably the most important thing. Okay, so derive it yourself, but it's pretty straightforward. So once you know the recursive relation, all you need to remember is that since this is not homogeneous, the upward recursion is completely trivial because you know k0, you can evaluate it. The downward recursion, however, is a bit non-trivial because it's non-homogeneous. Therefore, you need to have k for the largest possible n, and that can be done with Taylor expansion. Taylor expansion is something that you should also be able to do. It's pretty straightforward. So with this, I would stop for today. Next time, we're going to go a little bit more into details of Python language. So we're going to introduce Python language more precisely. We're going to go through lectures, which I prepared. No, this is mouse. This is not the right thing. So we are going to go through just a second, learning high level languages. We're going to go through this introduction, basic Python, NumPy, SciPy, and then some examples from SciPy, using SciPy with solving hydrogen atom with this algorithm. Yeah, and and then we're also gonna solve not hydrogen, but generic atom with so-called DFT approximation. So through this homework 3, homework 4, and so on. So yeah, with this we're gonna master Python SciPy pretty well, and then we can go to slightly more advanced algorithms. Any question about today's lecture?
Professor, you said we can work on this with our classmates, the homeworks?
Okay. Can you work with classmates? I was hoping you can do it yourself.
Well, I mean, just in general, not specifically this one.
Yeah, I don't know. I mean, coding needs to be done more or less by yourself. I don't know how this would help if you do it with somebody else. I mean, if you want to check with your classmates whether you have the same recursive relation, that looks to me reasonable. Of course, you can talk. I'm not gonna check whether you talk with your classmates, but I would expect you to code yourself somehow. I don't know. I mean, I'm not gonna run after you and check whether you talk to people. It's okay to talk to people. I'm not gonna prohibit you, but I do expect that you have unique homework in the sense that if there are going to be 2 or 3 homeworks that are going to look exactly identical, I'm going to be suspicious. Does this answer the question?
Yeah, that's fine. Thank you.
Yeah, so I expect everybody to write your own code, isn't it? Not identical. Okay, because if you don't code yourself, then you're not going to learn how to code. I mean, that's to me, it's pretty obvious that you have to practice yourself. It's not good enough to do it together. Homework due, yeah. So I usually give you 1 week for homework. So if today is 10th, so 17th, would that work? 17th?
It's fair.
Yep, it's okay. 1 week from now. Okay. So, yeah.
Professor, so for the optional part, I'm just curious, for the using the F2Pi routine
Yeah.
to speed up your code, we would have to write this in Fortran, right? And then
either on Fortran or C. And
okay,
then,
yeah. So if I have to use F2Pi, then I have to write it in Fortran and then have Python create an equivalent form.
Correct. Yeah, I mean, this is for your practice. I'm not going to even check it. So if you don't want to do, if you don't have time or you don't want to do it, it's okay. This is just if you want to practice yourself. Because I understand that most of you are not familiar with Fortran or C++, so this might not be that easy to do, doesn't it? Only if you're familiar with C and you want to practice, or if you're familiar with Fortran, you want to practice, then I think this looks a good thing. But otherwise, I understand that it's probably hard. I mean, we are going to go into details of Python later on. So in some sense, even the Python part might be hard for you to do right now if you didn't practice Python before. So therefore, in the worst case scenario, if you can't do any of those, you can at least do all the math on I don't know, in Jupyter Notebook or in LaTeX or something. So that I see that it is the math, you've done it yourself, and you try to do some coding, which might be a little bit buggy. I expect you to do something, doesn't it? At least your best guess how to do the code, how to write the code. Since we didn't practice so much the coding, I understand that some of you might not be able to write a code without a bug yet. Okay. Or look into the Bessel example and try to modify it a little bit. That's another possibility. Okay. Any other question?
Yeah, a question regarding the F2Pi and the pipeline 11.
Yes.
So I observe the code and I find there is actually not too many loops in code. So is that really necessary to imply the F2Pi or pipeline 11 too?
Well, okay. So my answer would be that you're not going to get enormous improvement of speed. You're probably going to get something like, I don't know, factor of 3, factor of 4. But the point is that Basal functions are extremely important for in many algorithms, and factor of 2 to 3 it's still relevant.
Okay.
I mean, I'm not saying that for this homework it's so essential. I mean, here we are looking at the algorithms mostly, not speed. So yeah, not that important, but still, if you want to build your own library, isn't it? Let's say that you want to do your own library, then I mean, Basal functions which are 3 times slower than what you can do is still important.
Okay. So if we want to do that, so we basically write a Fortran code and replace the for loop, right?
Yes.
Yeah. Okay. Good.
Yes.
It's not hard. Yeah.
So there's going to be a little subroutine. So where's my Basal? It's going to be a little subroutine. Basically, what would it be? This part, of course, needs to be.
Yeah.
But even this part, I mean, I will probably write the entire thing in Fortran.
Okay.
The entire thing, yeah, because then you're going to get the full speed. Or C++, of course. So, yeah, I guess the entire thing needs to be rewritten, yeah, because as you said, there is just one loop. So probably once you even start allocating something in Python, you're going to already lose the speed.
Yeah, and another reason is it's recursive, right? So the recursive is not very good for parallel computing.
Yeah. So
because you must wait for the last loop and use that as input parameters for your next loop, right?
You're absolutely right. Parallelization here will not work. What one could do, however, is you could allow X to be an array.
Oh, yeah.
And that's sometimes useful.
Okay. Yeah,
if X is an array, then you can make it parallel. That's completely parallel, completely independent.
Yeah.
Thanks.
Sure. Yeah.
that's something that might be useful. And actually, NumPy I think does allow arrays, and I'm curious whether NumPy then allows open-MP parallelization. It could be that it does.
Mhm.
I didn't check.
Okay, I will give a try. Yeah.
Yeah, I mean, again, don't. This is for your training. It's not essential, but it's
Mhm.
useful.
Mhm,
Practice.
sure.
Okay. Any other question? No. If no, I'm going to stop sharing and I'm going to stop my